Welcome you again to this course Fundamentals of Compressible Flow. We are in the module 4 normal shock waves. So, previously we have gone through 2 lectures in this module where we discussed about the formation of shock waves, what is its importance. We discussed about the fundamental equations and we derived one important relations known as Frankel relations for the normal shock, and based on these relations one can find out the flow property across a normal shock. So, we will move further from this contents, and we today in this lecture we are going to discuss some important inferences that we come across from this normal shock analysis. Now, apart from that, we are trying to introduce a theorem which is known as Crocos theorem. It is a very vital and important theorem that relates the fluid kinematics aspects with respect to thermodynamic relations that normally is encountered across a normal shock. Of course, this Crocos theorem has nothing to do with normal shock phenomena. Crocos theorem is independent in nature that correlates the fluid kinetic concepts to thermodynamic concepts. And in our study, that is in the normal shock analysis, we will try to see how this theorem is useful to us to describe certain flow fields across a normal shock. Now, having said this, we will now move to introduce a Grass property table for normal shock relations. So, previous lectures we derived the mathematical formulations of different parameters for a normal shock, but many a times these parameters are difficult to evaluate, and for which we have to refer to the property tables. So, I will introduce this Grass property table, how you are going to see the table to find out different values. Then we will try to see that how that gas table can be used to solve certain numerical examples. So, this is the broad outline for this lecture for today. Just to give the brief insight what we have learnt in the previous class, I can say that a normal shock is a very natural phenomena for a supersonic flow field, in which all the compression waves merge in a very thin region, and this thin region has a typical dimension of 10 to the power minus 7 meter. And across this thin region, all the flow properties before the shock and after the shock are all the flow properties needs to be correlated. So, and when you see this magnitude of this property, they jump in a very steep manner, or they jump drastically in one direction and across this discontinuity region. So, the given problem that we have is that we have a standing normal shock. So, the conditions that are upstream conditions are known to us, such as pressure, temperature, density, velocity, Mach number, all stagnation properties they are known, and what are the unknown condition is what happens after the shock wave. So, in our previous study we tried to derive the correlations between these properties value upstream and downstream across this shock wave. So, after doing so, we will try to find out, we have of course, we have derived so many parameters across the normal shocks. So, we will try to find out some important consequences. So, which I call as inferences number 1. So, first inferences that we can talk about is limiting Mach numbers. So, as we say see from this Frankel relations, which is the star conditions of M1 and M2 across a normal shock, they are inversely related, and from these relations we can actually find out the Mach number relations across the normal shock, that is M2 and M1. So, this is given by these equations. Okay. Now, having said this, we can say that how M2 will vary, with respect to M1. So, this says that if your M1 is supersonic, M2 has to be subsonic. So, it means that has to be subsonic. So, that means this is the first important relations what we get, but why M1 has to be supersonic, that will come back later when you do the entropy analysis. For the time being, let us say that M1 is supersonic. Now, when M1 is supersonic, the minimum value of M1 should be 1. So, when it is M1 is 1, M2 is 1, which means there is no shock wave, it is just a simple Mach wave or just a beginning of formation of shock wave. So, effectively the flow is, there is no shock wave, there is entire flow condition is isentropic. So, this is one case, that this is the what I can say the beginning condition of shock wave. So, we say that this is the first limiting conditions. Now, second limiting conditions, that how long I can increase M1. So, if I if I go on increasing the M1, we will find there is a upper limit of M2. So, M2 cannot be more than certain value. So, this we can see from these equations, like the relation between M2 and M1 can be also written in this form, that is M2 square is equal to 1 by M1 square plus entire bracket gamma minus 1 by 2 divided by gamma entire bracket gamma minus 1 by twice M1 square. Now, in this equation, when I put the limiting condition, when M1 goes to infinity, means this region, the upstream this condition 1 becomes when M1 goes to infinity. That means, we are putting a limit that we keep on increasing the Mach number and on the upstream side. So, what happens in the downstream, that this particular term, when at this condition we can say 1 by M1 square goes to 0. So, when I say 1 by M1 square goes to 0, in the expression of this M2, we can say this two particular term becomes 0. So, this leaves out the limiting case of M2 will be equal to square root of gamma minus 1 by twice gamma. Now, when we put gamma is equal to 1.4 for air, so this value turns out to be 0.378. So, when at this condition, when we say your M2 will be fixed by 0.378. So, in other words, the M2 value cannot come below this number, provided you are using air. That is first consequence, and that is the upper limit. Lower limit, M1 can be 1. So, will be M2 will be 1. So, this particular situation will let you know that the flow is isentropic and there is no shock wave. So, this is the first limiting case, this is the limiting case for Mach number. Then moving further, let us see what happens to static property ratio. By static property ratio, I mean static pressure ratio P2 by P1, static temperature ratio T2 by T1 and static density ratio rho 2 by rho 1. So, previously we have derived these relations across the normal circle, and all these relations are nothing but the functions of m1. So, looking at this equation, when what one can say that when m1 goes to infinity, the P2 by P1 and T2 by T1 also goes to very high value. So, there is no limiting case, because this equation does not restrict these numbers. But whereas interesting phenomena will happen for the density. So, when m1 goes to infinity, this unfortunately this term 1 by m1 square goes to 0. So, when 1 by m1 square goes to 0, the density ratio rho 2 by rho 1 turns out to be gamma plus 1 by gamma minus divided by gamma minus 1, and for gamma is equal to 1.4, this ratio has to be 6. So, here also I can say that m1 is equal to 1, m2 will be 1, but at the same time your this rho 2 by rho 1 goes to 6 when m1 goes to infinity. So, irrespective of what value of pressure temperature, the density ratio cannot be more than 6 for air, that is irrespective of Mach number. And next we will move to the third inferences, that is for the entropy conditions. So, in the beginning I told that we say that m1 is supersonic. Now, we will try to find out this answer why this m1 should be supersonic. So, these particular things can be answered from this entropy analysis. So, what we learnt so far, that from Frankel relations one can obtain Mach number relations across a normal circuits. So, the conditions for supersonic and subsonic and supersonic nature of the flow across the normal circuit is decided through entropy analysis. The static pressure, static temperature increases across the normal circuit. So, the entropy equation will demonstrate that the entropy change across a normal circuit is a function of Mach number. In fact, we derived this from our previous analysis. Then we will try to invoke that what the second law of thermodynamics tells us. So, the second law of thermodynamics tells us the important consequence, that is directionality of a flow. So, this flow will proceed in a direction in which the thermodynamic property, that is entropy, should increase. So, now to show that why m1 cannot be subsonic. So, first thing we have to see this particular important equation. This is the very thermodynamic fundamental equations, how we want to calculate the entropy change between two states 1 and 2. Now, that is S2 minus S1 will be Cp times ln T2 by T1 minus R ln P2 by P1. Now, this is the broad analysis. Now, we try to use these equations for a shock wave. So, we know this temperature ratio, we know the pressure ratios. So, when you put those expressions, this turns out to be this. Now, one thing important to be noted here, that when m1 is equal to 1, so S2 is equal to S1. This is what we say, that when m1 is equal, that we have said earlier, when m1 is equal to 1, m2 is equal to 1. So, this is S2 is equal to S1, then this is the entire isentropic, as if there is no shock wave. So, and in this equation, when you put m1 is greater than 1, we will find the S2 will be greater than S1. So, this is the conditions for shock wave that we have been analyzing so far. So, that for which we say that m1 will be always greater than 1, for which m2 should be less than 1. So, these two relations holds true. But if you see the third relations, what we will find out, that if m1 is less than 1, your S2 minus S1 will be less than 0. So, this does not follow the second law, that entropy decreases in the direction of the flow. So, this is a impossible situation. As far as the second law of thermodynamics is concerned. So, always we consider the relation which is written in the middle, that is m1 must be greater than 1. And also we can say that for subsonic flow entropy decreases across a normal shock, and hence shock waves do not exist in the subsonic flow. And again moving further from another inferences 4. So, here we will talk about what happens to the stagnation property ratio. So, one of the important relations from entropy change across a normal shock can be calculated as S2 minus S1 is equal to minus R ln P naught 2 by P naught 1. So, P naught 2 is nothing but the stagnation pressure after the shock, P naught 1 is the stagnation pressure before the shock. So, we can say that entropy change across the, and this P naught 2 is calculated from P 2 and M 2, and P naught 1 is calculated from P 1 and M 1. So, we can say that the entropy change is given by these relations. So, this says that P naught 2 should be less than P naught 1, that means stagnation pressure always drops. Why it always drops? Because in earlier analysis we have said that energy equation does not change. So, total temperature or stagnation temperature remains constant. So, having said this, and if you say the equation of state P is equal to rho R T, and for this case if you say P naught is equal to rho naught R T naught. So, if this equation has to be satisfied, then these two conditions must valid. So, stagnation pressures this is equal, stagnation pressure should drop. So, when this is drop and stagnation density also should drop. Okay. So, this is all about what we have studied from this analysis of normal shock and its inferences. Now, we will move to a theorem which is known as Crocos theorem. Just to start this, so let us forget that we are dealing with a normal shock analysis, but what we are dealing with just a fundamental theorem, and that is applicable for all situations that involves fluid kinematics and thermodynamics. And in particular, we are trying to apply this Crocos theorem for our compressible flow theory. So, what does this theorem tells? It is it tells about the relation between a fluid vorticity with respect to entropy change. So, when I say fluid vorticity, it is a kinematic parameter, and when I say entropy, it is a thermodynamic parameter. Now, what it tells is that, so when I say fluid kinematic parameters, the common parameter that I should know is about this angular velocity omega vector, okay, then velocity vector, okay, and another parameter what we will say vorticity vector. So, vorticity vector is nothing but twice omega vector. Okay. So, now we know that from fluid kinematics analysis we can say that angular velocity vector can be is equal to half times gradient cross velocity vector. Okay. So, this is how we these fluid kinematic parameters is defined. So, what we are trying to see here is that we are Crocos theorem, which is given by this particular expression, velocity vector cross product bracket gradient cross velocity vector bracket end is equal to gradient of H naught, that is total enthalpy, minus T gradient of entropy plus dou V vector by dt. So, this is a vector relations, and to derive these equations. So, let us start with the equations that we can recall. This equation called as Euler equation, but in vector form. So, when I write this Euler equation in vector form, what I can write, rho dou V vector by dou t plus rho then V vector dot gradient into V vector is equal to minus gradient of P. So, what I can write is, we can find out a term, this gradient of P divided by rho will be minus of dou V vector by dou t plus rho V vector dot grad into V vector. Fine. Then also we have to recall a TdS relation, that is the in vector form. So, one thing I need to emphasize, this Euler equation is a fluid parameter term, TdS relation is for the thermodynamic term. So, what I can write, T gradient of S is equal to gradient of H minus gradient of P by rho. So, here we also know that gradient of P by rho from these Euler equations. Also we know H naught is equal to H plus V square by 2, that is total static enthalpy plus V square by 2 is stagnation enthalpy. So, from this we can find out what is gradient of H. So, once you do that, so you have to do some mathematical jugglery. So, you put this gradient of P by rho in these TdS relations. So, what I can write, T gradient S is equal to gradient of H naught minus gradient of V square by 2. Now, from this minus gradient of P will be plus d V vector by dt plus rho will not be there, rho we have taken this down. So, we say V vector dot gradient into V vector. So, here we have to know certain mathematical relation, what we call as vector identity, that relates between these two parameters. So, what we write is gradient of V square by 2 is not minus V vector dot gradient into V vector is nothing but velocity vector cross product gradient cross velocity vector. So, this is a mathematical derived term. Now, when I put this vector identity equation for these two terms in this equation, then we write this TdS relation as T gradient of S is equal to gradient of H naught plus dou V vector by dou T minus V vector cross gradient cross V vector, right. Now, after rearranging one can obtain this particular relation written in the first equation. So, if you look at this equation, it contains all these terms that relates the one side of this equation contains the kinematic parameter, that is velocity vector, other side of the equation contains the entropy term, temperature and enthalpy term. Also there is another parameter which is a unsteady parameter, dou V vector by dou T. So, this equation I can say it is for unsteady flow and when for a steady flow this term this term will vanish. So, this becomes steady flow. Okay. So, this is how the equation that is for Crocos theorem equation are defined by these two expressions. Now, let us see how this Crocos theorem is useful to us. So, now let us say if we are talking about a shock wave and we are trying to correlate the fluid parameter with respect to thermodynamic parameters. So, here we are talking about the H naught, that is delta H naught, and that is nothing but delta Cp T naught. Okay. So, that does not change because total temperature across a shock wave is remains constant. So, delta H naught is 0. Now, what happens to entropy? Delta S S2 minus S1 always greater than 0. So, that means entropy gradient of entropy cannot be equal to 0. So, this says that your curl of velocity vector cannot be equal to 0. When curl of velocity vector cannot be equal to 0, this turns out to be omega vector cannot be equal to 0, which means that when I say shock wave, thin region of the shock wave, the flow field in this thin region is highly rotational. Which means if you visualize the flow field, we will find these fluid elements try to have rotational vectors in this thin region. So, across a normal shock the flow is highly rotational. This is one of the important inference that a shock wave analysis gives to us. Okay. Now, whatever we have summarized, whatever we have learned so far, if we want to summarize normal shock relations, we said about the Frankel relations that relates between the shock Mach number before the shock and after the shock. So, very basic bottom line is that if you have a standing normal shock, the conditions that are known to us is the upstream conditions, all the flow parameters are known. The conditions that are not known to us as the all the downstream parameters. But what we know simply is the relation between Mach numbers M1 and M2 through these Frankel relations. Now, using these relations one can find out all the pressure ratio, static pressure ratio, static density ratio, static temperature ratio, and if you see here all these number will increase. So, in fact, we also can have stagnation pressure ratio that drops, total temperature is equal. So, in this way we can calculate. So, one way of looking at this equation, if you see all these ratios are the functions of Mach number and which is in the upstream regions, which is known to us. And every time if you know the Mach number, every time it is almost a time consuming task to use these equations to know the flow parameters. So, one convenient way of looking at this approach would be create a database in which we will vary M1 and try to find out what are the how the ratios will behave. So, so in this way a table can be prepared for a normal shock and we call this as a gas property table for all the normal shock and relations. So, by that table we will try to avoid the time consuming task of calculating the flow parameter using these equations. Now, let us see how this table is framed. So, for this table I have taken this extract from this reference book John D. Anderson Modern Compressible Flow, that is McGraw-Hill publications. So, this is one such of extract what I have just taken. What it says is that this has about 7 column of data. The first column belongs to the Mach number which is upstream. So, for the normal shock the first column that talks about is M1 and the last column is M2. So, across a normal shock I know what is my value of M1 and correspondingly the last column will talk about what will happen to the M2 conditions. Okay. Similarly, if I know if my pressure ratio if I want to calculate, if it is P1 and if it is P2, so second column will give the pressure ratio across the normal shock. If your density is rho 1 and rho 2, the third column will talk about the density ratio which is the function of Mach number. Fourth column will talk about the temperature ratio T1 and T2. Fifth column will talk about the stagnation pressure ratio. The stagnation pressure ratio, that means for corresponding P1 and M1 we can define a stagnation pressure P01 and for M2 and P02 we can define the stagnation pressure P02. So, that ratio is given by this P02 by P01. And also there is another relations, once you have this P01 and we can also correlate with P1. This is another important relations, we call this as Rayleigh-Pitot equations. So, this is many times this ratio is also very important which we can directly find out from the gas table. So, what we can see that there are 3 regimes just I have written. First regime is we can say the first value that stands as M1 is 1, that is what we say, and this M1 can goes to infinity. So, here it has been plotted about 17, Mach number of 17. Until now this is the realistic number what we can say. So, the first part of this is can say it is a low supersonic, middle one is in the range of maybe supersonic, the bottom one is very high supersonic, and we call this as hypersonic flow. So, these are the I mean there are any number of intermediate data that can also be generated. So, this will just give you a glimpses that how a gas property table looks like. Now, looking at knowing on this, we can find out all the parameters. So, with this let me demonstrate that how one is supposed to refer this gas property tables. So, for that let us solve some numerical problems. The problem that is given to us, that we have a standing normal shock in the test section of a supersonic wind tunnel. It has the parameter that is upstream, for which the Mach number is 3.5, static pressure ratio is 0.4 bar, and static temperature is minus 70 degree centigrade. So, we have to calculate the Mach number, static pressure, static temperature, velocity downstream of the wave. So, if you want to solve this problem, so first thing we have to draw a very schematic sketch that briefs about the problems. So, if you have a normal shock, what we know is upstream, which is M1, that is 3.5, static pressure P1 0.4 bar, static temperature is T1, that is minus 70 degree centigrade, or we can say 203 Kelvin. What we do not know is M2, or that is what is required to calculate is M2. It requires to calculate what is P2 and T2 and U2, right. So, one way to look at the problem is that you take all these standard relations, use your calculator and calculate all these parameters, M2 by M1, P2 by P1, because M2 will be function of M1, P2 by P1 will be function of M1, all these numbers are known to us. But what I am trying to say is that how to use the gas dynamics table. This is one such extracts from this gas dynamic table from the book, where I can get the information about Mach number of 3.5. So, if you look at this, the first row on this things says that Mach number of 3.5, it talks about all the parameters. So, I can write this when M1 is equal to 3.5, then I can say P2 by P1 is 14.12, rho 2 by rho 1, in fact rho 2 by rho 1 is not required to us, T2 by T1 we say 3.315, we also require Mach number. So, we can say M2 will be 0.4512. So, we require P2. So, P2 can be written as P2 by P1 into P1. So, we know P1, we know P2 by P1. So, P2 can be calculated as 14.12 into 0.4. So, it is about 5.65 bar. Similarly, T2 will be T2 by T1 into T1. So, this will be if you calculate 3.315 into 203, 673 Kelvin. So, what is left out? We know M2, we got M2, we got P2, we got T2, we want to U2. So, U2 will be M2 A2. So, that is M2 A2 will be square root of gamma are T2. So, we know M2, we know gamma, we can say M2 will be 0.4512 square root of gamma 1.4 R 287 for air, and T2 will be 673. So, this will tell you that U2 will be about 235 meter per second. So, this is how we look at this problem. So, we get all the parameters by using this table data. Okay. The second problem we will try to see in another way of look at the problem. A blunt nose missile flies at Mach 2.3, calculate the pressure and temperature at the nose of the missile. So, in one of analysis is a blunt nose missile. So, a blunt nose missile is something is represented in this manner. Nose is a blunt. So, when for a blunt nose missile, when it is flying at 2.3 Mach, it will have a shock wave sitting onto this body at the nose. So, what we want to see is that at the nose of this, we can zoom this version, we can assume it to be a normal shock. So, when it is a normal shock, so upstream condition we can say that as if a gas is moving or moving from upstream to downstream, for which your M1 will be 2.3. And if there are two situations it is asked, when for this M1 is equal to 2.3, what we require is pressure and temperature at the nose. What we require, okay. So, at the nose of this, what we see here, the flow happens to be almost remain stagnant, because if this flow comes at this point, this flow is almost stagnant. So, that part we say that on a blunt nose body, at the nose of the missile we will encounter a normal shock, and the whatever pressure and temperature, that will be nothing but your stagnation pressure. So, for that what we want to find out, what is P naught 2, what is T naught 2. So, here the confusion may arise, what pressure we should find, static pressure or stagnation pressure. But here your answer should be stagnation pressure, because a blunt nose missile always encounters stagnation pressure at the nose, because the flow tries to comes down to almost rest at that point. And second assumption what we are doing, at the nose portion the shock wave will be close to a normal shock. Now, this is the things we require, but what the conditions that is given, there are two situations. So, we have to find out one at sea level conditions, other is at altitude 18 kilometer altitude. So, means that the missile is flying at, if a missile is flying at sea level, what will be the P naught 2 and T naught 2? If the missile is flying at 18 kilometer altitude, what will be this value? So, to that we require a sea level pressure. Sea level pressure is normally represented in a static value. So, I can say P1 to be 1 bar and T1 to be maybe 15 degree centigrade or 288 Kelvin. Similarly, from the data table we can, or maybe if you look at the property data, altitude versus pressure temperature, then we can find out that at an 18 kilometer altitude the pressure will be very low, 0.74 bar, and temperature is about 218 Kelvin. So, there is a drop in temperatures with altitude. So, to do that what we so at sea level situation, if you want to calculate, then what we can find out, the first relation, that is we require, we know P 1, we want P naught 2. So, basically we have to refer this particular column of this table. So, for this particular column and Mach 2.3, I have to refer this particular row. So, I can get this number to be, we can say for M 1 is equal to 2.3 will implies P naught 2 by P 1 would be 7.294. So, from these things one can evaluate what is at sea level. We can say P naught 2 would be pressure is 1 bar. So, it will be 7.294 bar. At 8 and at that point you can say temperature, okay, and at 18 kilometer altitude we can say P naught 2 will be 7.294 into 0.074. So, this much bar. So, this is how we get pressure. Now, to find temperature, what we require, because what we can say, temperature across a normal shock do not change. So, I can say T naught 2 is equal to T naught 1, but T naught 1 I can find out that T naught 1 by T 1 is equal to 1 plus gamma minus 1 by 2 m 1 square. This we get from isentropic relations. So, for m 1 is equal to 2.3, this ratio turns out to be 2.06. So, we can say T naught 2 at sea level would be 2 or T naught 1 would be 2.06 into 288 Kelvin, that is at sea level, and at 18 kilometer altitude we can say T naught 2 will be T naught 1 is equal to 2.06 into that point your T 1 is 218 Kelvin. So, this analysis tells us that when you go with altitude, the total the pressure drops. So, what you can imagine that at sea level, if your pressure is close to 7.3 bar, but it drastically reduced to a very low pressure at that altitude. Since your drag will be less, and that is the reason one can fly at very high speed, high Mach number in higher altitude. In fact, temperature will also be less. Okay, this is all about the problem number 2. And problem number 3, this is again a similar problem, which we say is that Pitot tube is inserted in a supersonic flow and is measures 3 bar pressure, while static pressure is 0.4 bar. We require Mach number and entropy change. Here The entire idea as mentioned that pitot pressure, the pitot probe measures stagnation pressure. So, across a pitot press there will be a close to a very normal shock. So, across the normal shock the pressure is measured to be 3 bar, that is P naught 2, and the static pressure in the flow field is 0.4 bar. So, one should not confuse that this pressure is a static pressure, that is 0.4 bar, and pitot, when I use the word pitot probe, then I must use this as a stagnation pressure. Now, which stagnation pressure? So, this has to be stagnation pressure after this normal shock. So, when I say after the normal shock, then it must be P naught 2. So, when I say this, when I know, when I infer the data, then I can say, I can easily calculate the ratio P naught 2 by P 1. This ratio is about 7.5. So, to do that I have to refer this data, because I do not know the Mach number, but Mach number you want to find out. So, from this table we have to find out in this column of P naught 2 by P 1 which data is close to 7.5. So, take the extract from that, then this number turns out to be M 1 is equal to 2.35. So, this will tell M 1 is 2.35. So, when M 1 is 2.35, what you require? Entropy change. So, entropy change will be S 2 minus S 1. One can use simple relation minus R ln P naught 2 by P naught 1. And for this Mach number of 2.35, this ratio is 0.5615. So, when I put this, I can write R is minus 287 ln 0.5615. So, we can write this S 2 by S 1, one can calculate it is 165.6 joule per kg Kelvin or 0.1656 kilojoule per kg Kelvin. So, this is how we can find out the Mach number. If Mach number is not given, this is the most advantage part of the using data table. Even though the Mach number is not given, but still we can, given the data of property data, we can also calculate the Mach number. This is the another way of visualizing the advantage of graphical or data table for property calculations. Okay. So, in this way I have just given some sample example how to use the data table for normal shock applications, and in fact one need not have to remember the big expressions of flow equations, but one has to understand that such equation exist, and in fact all these data tables are derived from those relations. So, with this I will conclude my lectures for today. Thank you very much for your attention.